to maybe a foundation for organic chemistry. I really do think, though, if you are a science major, chances are a lot of you will take not only chemistry, you might take biology if you're into more of the medical sway. And I think you'll find this to be helpful even in the biological world that you have there. So, all right, everybody ready? Sort of ready? Are you sort of ready? Sure. Okay. All right. So what we did was a quick review again. Remember one time that the idea of organic meant that they thought that at one time the only time you could make these funny compounds, these organic compounds, was you had to be a living thing had to make them. Either it was part of a living thing or a living thing made them, and then they found out, wait, we can actually make these out of non-living things. And so then organic chemistry really, in the late 1800s, really started blossoming, and they started discovering all kinds of things. Early 1900s, they really boomed. Now it's huge. It's just a huge industry. There's probably, I don't think they'll ever run out of slots for organic chemists if you want to be an organic chemist. So there's so many industries that would hire you. And around the world, there's, they're research chemists, but some people actually work for big companies, and they enjoy it quite a bit. Okay, we also talked about different things. One of the things they'll do in college, if you take organic chemistry, is you have to learn some of these mechanisms. Mechanisms are, hey, there's 5 steps. If you want to put 2 chlorines and 1 fluorine on a benzene ring, you want them in a certain order, then this is what you do. Click, 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 click. And then you have to memorize those steps, which, I didn't necessarily like that, but that's part of organic chemistry I didn't necessarily like. But I understand it. If I became an organic chemist, I would want to know how to do that. Like this one, what do we call that process? What does it even look like? I'm going to cover that up. What does it look like you're doing there? Yeah, that's it. What's hydrogenation mean? So you're trying to force hydrogen atoms onto some organic compound, right? And so this double bond gets broken, and you end up having all single bonds. That's pretty neat. The author thinks you've never had anything about organics, so he talks about structural isomers, and that's the only isomers I've even taught you about so far, right? Structural. And then we had naming, and we started talking about how they really do name them, and they have rules. If you want to read the rules, I've kind of been trying to teach you what they were. And I think what you need to do is, and I doubt whether this weekend, I just can't wait to memorize these different branches. So I doubt whether that happened. But you need to memorize these different branches, okay? All right, what's the easiest one? CH3 is what kind of a branch? Methyl, that was easy. What about the CH2? That was pretty easy. How many ways can you be a propyl branch, though? You see that? You can have 3 in a row. That's just called propyl. And then the one that branches is called what? Isopropyl. Okay, that's not bad. And then we have butyl. How many ways can you do butyl? Now I'm gonna stop at butyl, by the way. See that? Can you see this? Plain 4 in a row, butyl. What's sec-butyl? What does that stand for? Sec. Anybody know? Sec-butyl means that the branch, the carbon that's the branch is attached, that's attached to the branch, is attached to 2 other carbons, so it's a secondary carbon. And here, the tert-butyl down here, this carbon right here is attached to 3 other carbons here, so it's called a tertiary butyl or tert-butyl, like that. And this is one I always have trouble remembering. It's isobutyl, and it's like a fork, like that. They draw it like this. I like to draw it kind of like that. So anyway, take a little bit of time and just say, all right, once I learn those branches, then I can start naming lots and lots of things like that. All right. Let's see. Now, I'm hoping that the second half of the period today, when you guys are starting to do isomers, I think last week on Thursday, some of you thought there were how many hexane isomers? Somebody thought it was 6, is that right? And there was at least 2 tables said 6, some said 5. And so what happens if you start to name them, you'll see that 2 of them would have had the same name. And then that would have dropped it back to 5. So I think that's good to have you draw them and then you try to name them like that. All right, let's look at another reaction that an organic chemist might do and see if you can figure out the name of this one. Now, I didn't develop this one. This is easy. That's combustion. You know what combustion is. What would you call this right here, where it looks like they're trying to replace all the hydrogens of methane and say, I'm going to put on chlorine. I want chlorine to take the place of hydrogen. And I didn't do this, but somebody figured out you need UV light, ultraviolet light, and if you do that, you can replace 1 chlorine at a time. So this would be called chloromethane, dichloromethane, trichloromethane, and then tetrachloromethane. Anyway, so somebody figured out that UV light was enough energy to do that. I didn't do it. You'll find on another page somebody figured out there was a catalyst. Sorry, I couldn't think of that. A catalyst of some weird chemical that was a catalyst, and somebody discovered that. All right, what would you call that? What do you think you would call it? Because you can do the same thing with chlorine and fluorine and bromine and iodine. What would be a great name? It means you could replace hydrogen with any of the ones in group 7 up here, 7A. What would be a great name for that? Anybody want to take a guess on that? Think about all the elements in the chlorine, fluorine, bromine, the whole family there. You can do the same thing with any of those. What would you call that process? It makes you sound very smart, but what is it? That's it. Halogenation. Halogenations would be to replace hydrogens with one of the halogens, okay? Very good. Halogenation. Okay, then. All right. Show you one more. Wait a minute. No, not there. Okay, take a look over here. This page, and all I'm doing is you're supposed to be reading this. I'm trying to just kind of hit the highlights here. What would you call, oops. It's hard to cover that one up. What would you call that process right there? And again, I didn't, discovered that if you had chromium 3 oxide, and you heat it to 500 degrees. I didn't discover that, but somebody said 500 degrees, chromium 3 oxide, and you can change that into that. What would be a good name for that process? What do you think? Making all these little fancy words like halogenation, hydrogenation. What would this one be called? Look what they're trying to do. They're trying to make where single bonds are. They're trying to put a double bond, aren't they? But how are you going to do that? Say it again. Dehydrogenation. Wow, I got to know what that means now. Dehydrogenation means I'm trying to get rid of hydrogen atoms, and in this case, it's going to form a double bond, isn't it? So you could turn an alkane into an alkene. Okay, I got that. All right, what about the names for cyclic alkanes? We did that before, remember that? There are no cyclic, you can't have cyclomethane, you can't have cycloethane. Can you have cyclopropane? Can you have cyclopropane?
Yes.
What? Like this drawing right here? Can you have cyclopropane? Yeah, couldn't I? Now, what kind of angle would be formed between the carbon and carbon? I know it's Monday. I get it. It is Monday. But what do you think? What kind of bond do you what kind of angle do you think is happening here? Wow. Like, it's an equilateral triangle, isn't it? 60 degrees. Is that good? Is that a good for a molecule? Said, I like that. I like that 60-degree angle. Is that really, really close to the tetrahedron angle? No. They don't like that. That's strain. That thing's going to be very reactive. It's going to have a tendency not to want to be cyclopropane. You get that? How about cyclobutane? What kind of angle would that be? Okay. What do you think about cyclobutane? 9 degrees? Oh, we're getting closer. Getting closer to tetrahedral angle, but there's still kind of a strain there. What about cyclopentane? You remember your geometry class? Let me show you a little lesson just in case you want to remember this. What if I said cyclopentane? Does anybody know what angle it is if you have a pentagon, what the inside angle is? Did they ever teach you that, how to do that? I'll show you. How many triangles can you make out of this?
Can you choose the book
Oh.
over?
How many triangles can you make out of a pentagon? 3. And each triangle has how many degrees in it? Okay, how many angles do I have here? Is that it? Ooh, that's an easy way to remember that, isn't there? So each of these angles is going to be about 108 degrees, and that's a nice angle there. That's a nice angle. Anyway, this one happens to be, I'm hoping not, is this let's see, 1, 2, 3, 4. Cyclohexane, is that what this is? And anyway, they make a little point here about cyclohexane. And they said, well, that one's actually kind of stable. When you get an angle, something like that, it gets to be kind of stable. And they make a strange point. I remember when I was in organic chemistry, which is over 45 years ago. That's hard to believe I remember anything back then. But I do remember them talking about, I had no idea what they were talking about. I had never built models, and I ran out of carbon atoms, so I can't build it. I'll build it for you tomorrow. If you take cyclohexane, there's a little bit of an overlap of these bonds. And because they really want to, they want to be relaxed a little bit more, so instead of it being completely flat, it kind of puckers it. And so here's this cyclohexane, and it says, oh, and sometimes it goes like this, oh, and it makes that noise and everything. It goes, oh, all right, I just made it up. And so sometimes the two ends buckle up and go, oh, like that. And then sometimes one goes, oh, one goes like this, one goes like, oh, okay. And so one buckles up like this, and one buckles like that. Yeah, here's the rest of it, see? So they, but I remember them mentioning this many, many, many times. And they called them the boat and the chair. Now, I don't know, can you see the camera very well? No. Now, this cyclohexane, I even put a little person there, see? Okay. So the boat means that the cyclohexane, the ends kind of went like that, and I call that a boat. I guess it would look like a boat. And the other one is kind of laying over like I'll go down, you go up, or I'll go down. Anyway, here's the flat part, and then I'll flip up and you flip down, and they call that a chair. Oh, well, that's a minor thing, but said here in nature, it just so happens, at room temperature, 99% of all the cyclohexanes are share. They even had a theory about that. They saw that the electrons here, the negative electrons here and here, they would tend to interact and tend to push each other away. And the furthest away those could be is if I go that way and you go that way. Okay, now I don't know if that was worth 2 minutes of your time, but that's called the boat and the chair, and that's for cyclohexane. So if you're reading this and you said, I don't know what the heck they were talking about, that boat and chair, I can make that for you tomorrow. I didn't make it today. And there's one more thing I want to get into before we get back into isomers. Let's go over here. Let's see if we can name these. And it said here that when you're naming them, the ring is numbered to yield the smallest numbers possible. Remember that? We talked about that? So let's take a look, and let's see how, don't look at the answer if you don't mind. Now, do you see a branch here? And do you see a branch here? Okay, what's the last thing that should come out of your mouth? What do you see right here? Cyclohexane. cyclohexane, is that right? Now, so what's the name of this branch here? Uh-oh. What do you think? Propyl? If propyl would be CCC in a row. There are two propyls. What is it? Don't look at the answer. What kind of branch is that? Not regular propyl. Propyl would have been boop, boop, boop. Isopropyl. What's this guy? Methyl. So let's start naming, okay? Now, if we're going to name these, in this case, we want the smallest number possible. So I'm going to, if I number this carbon 1, and then I go this way. Let's say I go counterclockwise. 1, 2, 3, 4, 5. Is it 1, 5? Is it 1, 5? Or let's go the other way. 1, 2, 3, or 1, 3. So which way should we name it? Okay, now, since these are in a ring structure, they like the alphabetical thing. And so in this case, what's the name of this guy? And what's this guy? Isopropyl. And that's iso I, and this is methyl M. So we're going to call you first. So here we go. All right, so the last thing out of your mouth is cyclohexane. Okay, we got that. And they're going to say 1 isopropyl, 3 methyl, cyclopropane. Cyclohexane, I'm sorry. Sorry. So here's cyclohexane, 1 isopropyl, 3 methyl, cyclohexane. All right, you try this one. Don't look at the answer. See if you can try it. I really do need you to read this. So they have a lot of good examples in the book, and you're kind of getting a feeling for how they name things, the real way they name them. All right, what do you think? Did everybody say cyclobutane? Is that the last thing out of your mouth? Okay, now, what are your numbers? 1, 2, 3, 4? 1, 4? Or 1, 2? And are you going to start here and go there, or here and go there? What's the name of that branch? Ethyl? Propyl. So what are you going to say? Ooh, man, I'm sounding like a chemist here. See this? You okay on that? Okay, now, I'm going to do one more thing before we get into whiteboard groups. What happens when you start looking at alkenes? What do you think's going to happen? What's something that big that could happen here? What's the name of this thing? Whoops. What's the name of that thing? Everybody should know that. Ethene, right? Ethylene? Same thing? Okay. That's just it. And there is no other name. And there's no more isomers there, right? Or are there? No. Okay. Let's go over here now. And they make a big deal about this. They said, remember how we had conformations when there were single bonds, how they could bend, you know? And what happens with a double bond? Are you going to be able to bend and twist and what do they say here? They say, yeah, single bond you can do some twisting, but double bond, nope. Now, so what that is, and I'll show you how to name it. What you have to do is you have to find the longest parent chain that includes the double bond, and try to put the double bond in the lowest number situation you can put it in, okay? Now, before we do that, we have come into a new kind of isomerism. Before, we only had structural isomerism, right? Here's a new one. All right, I did make this model. Can you see this? All right, see the double bond? Now, I purposely didn't draw all these other hydrogens. I don't want you to pay attention to those. So here's the model down here, and here's the model right here. So I drew both those. Now, tell me what you see there. These look identical, don't they? I mean, don't they look like they're pretty much the same? Yet You know, you got carbon, 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 and but see what happens is when they can't twist, if they can't twist, the double bonds lock in something like this. See how this guy goes up and this one goes down? See how this hydrogen's here and that hydrogen's there? No matter what I do, I can't make them match. So they actually do have different properties. And somebody decided we were to talk about these kind of isomers. Okay, so can everybody see it right here? They're called the cis and trans isomers. And so let's talk a look at that. How in the world are you supposed to remember that? Well, trans has always meant to go across, like transport or like that. So trans and cis is on the same side. So let's take a look. These right here and these are on the same side. So this is your cis isomer, and these are on opposite sides of the double bond, and so are these, and that's your trans. So that actually happens when you start having double bonds. You actually have to watch out for cis and trans isomers. All right, so let's try one. Let's talk about this. Let's make this one, all right? Let's name this one. How would you name this one? And you say, well, 1, 2, 3, 4 carbons, so I'm probably going to say butene. But is that the only butene you could make? Is that the only way to make butene? What do you think? Okay, so most of you figured out you could probably do this, couldn't you? Could you do that? Now again, putting it here is the same place as putting it here, isn't it? But I could put it here. So I have two kinds of butene. So, what's your name, butene? What are you going to call this guy? What they did here is, if I start here and number it this way, that's better than starting this way, isn't it? See, if I start this way, I'm between 1 and 2. If I go this way, 1, 2, 3, 4, then it's between 3 and 4, isn't it? And I'm going to have the lowest number. So what would be a good name for that? Are they going to call it 1,2-butene? Or what did they decide to do? What is it?
2-butene.
What is it? Is that what you meant? No.
No.
So it's between number 1 and 2. So what did they decide to call it? The lowest number, 1-butene. This one's between what? 1, 2, 3. He's between 2 and 3, isn't he? So what are you going to call him? 2-butene. All right. All right, 2-butene. Now, would I have cis and trans isomer here, and would I have it here? Let's think about it. I'll even draw the hydrogens in there, and here's your double bond, and here's a hydrogen, and hydrogen, hydrogen, and matter of fact, I don't have another hydrogen here. So even if I rotate it around there, what about this guy though? What about here? What if this has a hydrogen here and this has a hydrogen here? Would that be different than? What if I put a hydrogen up here and a hydrogen down here? What do you think about that? Would that be the same? It looks like it would, but they can't twist there, can they? So we actually have 3 isomers of butene. I'm not actually done, but 3 isomers of butene that look like this. And this you wouldn't have to worry about cis and trans isomer. I don't even have anything here anyway. But here I would have to worry about, here's cis and here's trans and 2-butene. Now, is there another isomer of butene? Now, I know it's Monday, and it's like, well, I don't know. I'm thinking about atheism right now. That's my class, my worldview class. What do you think? Is there another isomer of butene? What's the formula for butene? C4H. What's that general formula? What is it? Is that right? All right. Is there any other way to make C4H8? Calvin, you're shaking your head. What is it?
Is it C double bond to C?
C double bond what?
C double bond to C.
Okay.
Bond to wait. Could you do like a cyclo?
Okay, wait. Wait.
That's what I was gonna say.
And we were building models. Remember that the price you pay for putting a double bond in is the same price you pay for a ring structure, isn't it? So you can actually draw another one. What about that guy?
Wait, no, shoot,
Will that be it?
there's
Wow. So that, wouldn't that do it or not? And that's what's that called? Cyclobutane. Ooh, cyclobutane is an isomer of butene, isn't it? All right. Wait. That might be enough. Let's see. Yeah, I think that's enough for that. Anyway, don't be. Try to keep going. You know, if you're reading about 5 pages a day, or maybe if you skip a day, then probably try to read 8 pages, and try to keep up with the book if you don't mind. All right. So now what we're gonna do is we're gonna get into whiteboard groups again, and I'm gonna have you start again with the isomers of hexane. And then when everybody agrees how many there were and what the names are, then we're going to move on to heptane, and then we're going to try octane. That'll be the biggest challenge for you so far. But let's go ahead and get in whiteboard groups. And don't mind spread out a little bit. The tables, there's 4 different tables you can be at. If you want to sit with somebody else today, you can do that. I'm bring the camera over here so you maybe see them watching building some isomers, okay? I want to have a bigger one. Might need a big whiteboard.
So is cyclobutane isomer?
Yeah, of C4H8.
Even though
So there are three isomers of C4H8 have the word E in it. One of them does not have E in it. All right, here we go. Isomers of hexane. Isomers of hexane. Here, get this out of the way. All right. We're doing the boat and chair thing. They're fuckering out. There, Alan says hi to everybody. Hi. Alan, they're going to try to do all the isomers of hexane. And then they have to name them. We're going to come back. So build the backbone and then name them. Build the carbon backbone and then name them. Oh, good practice. Good job.
just write out the isomers, I guess. First.
So you do all the ones that are 6 in a row,
I'll just write them all.
and you exhaust all the ones that are 5 in a row.
Like write all the isomers and then
There you go. They're off to a really good start.
Wait, that's the same.
Oh yeah.
Oh yeah, sorry.
No, it's not. Once the middle will get it.
And then you can do.
4 in a row, 2 branches.
So you got your 6 in a row, you got your 5 in a row. Have you exhausted all the 5 in a rows? There's no more methyl pentane.
It's the same.
I might-
I'm sorry, I got
No, you can do.
I'll leave a little space so you don't, because somebody's got to put a name underneath these only.
Oh, yeah, that'd be the same thing then.
You do 4 in a row with.
And put N-hexane for, if it's straight chain, it's N-hexane. Does that say 2-methylhexane?
This one, yeah.
Shouldn't be 2-methylhexane.
No, it's 3.
couldn't be that anyway. That's hexane. The longest parent chain there only has 5.
2, 3, 4, 5, so it'd be pentane.
Say like this name is same as this one.
Well, I think it's wouldn't it just be
Alright, you gotta-
That's what I
I
was
bet
just-
you exhausted all the ones that were 6 in a row.
We just put the numbers.
How about the 5 in a rows? How many 5 in a rows did you have?
2,
2? Okay, that looks. How many 4 in a rows?
2,
2, where they at?
here and here.
Okay, how about 3 in a row? Uh-oh, what happens when you have 3 in a row?
It would just be.
Would there
It's a
be any of
It
confirmation?
would
these?
be like 3.
Would any of these have the name propane?
No.
No.
Okay, so what happens when you have 6 and you only want 3 in the parent chain? What happens to the other 3? What are you gonna do with them?
It's just like would bend
Did
them.
you try it? Did you try 3 in a row?
It would end up being like.
Now start putting 3 more carbons somewhere, and you said, "Oh, 3 more." Now that's turned the corner, so that won't work. So get rid of that one. That's not a branch. Let's put 2 in the middle. Oh, wait a minute. Now the longest chain is 4. I have that one. So put another carbon up there. Now, did you have that one before? I don't see that one.
Aren't there only 5 though?
I have that
Okay,
one.
all right, name them and see if any of them have the same name. All right, we got
You put 2 twice. It's gonna be 2.
N-hexane, 3-methylpentane. That looks good.
2
Is that
how you do it?
all right. Okay, so you found out. Oh, look at that. Okay, is that the only pentane you can have? There's only one pentane.
I think we have one further down.
Well, don't do that. Just put it somewhere else. If there's another one, put it somewhere else. But
So there's another container.
see, here's what messed you up a little bit. When you bent the corner, it's messing your mind up a little bit. Because couldn't I have put this carbon here, right here?
Yeah.
But if you,
We didn't know we were gonna write down pentane. We just kind of drew
Oh.
it out first.
Okay, let's do this then. Oh, bad. Okay, so let's put one here. Wait, the one you have is this guy, isn't it? Why don't you put it here instead? What about that?
That'd be
What's that called?
2-methylpentane.
2-methylpentane. So they're actually 2 pentanes. And this guy is butane, and that's the only way you make butane.
No, because we got that one too. That'd be
Now,
2.
be careful on this one because watch, I'll turn the corner. 1, 0. That's butane. That's 2,2 dimethylbutane. That's the same one as that guy. That's repeat. All right, how many? Give me your final number. How many?
There should be 5.
5? What do you think? 5? What do you think? How many? 6? If you put names on there and they have the same name, you're gonna have to change your answer.
Okay.
How many isomers?
We got 5.
5? No more? You sure?
We're still working it.
Okay.
So then 2-methyl. Caleb, how many did you get?
There are 5.
So what is it?
Put N-hexane when you have a straight chain. N-hexane.
2 dimethyl.
So there's 1 hexane, and there are 2 that are called pentane. And so now you go to butane,
Hold on. Could this also be?
and you gotta be careful because look at this here. 1, 2, 3, 4, 5. That's a pentane. That's 3-methylpentane.
That's butane right here.
Yeah.
And what's this right here?
This study.
1, 2, 3, 4. 1, 2, 3, 4. That's the same name. All right, go ahead.
Oh, would this be 2, 3?
Yeah.
This would be 2, 3. This would be different than 2,
3.
Oh, butane. Try this butane.
Yeah. So 1, 2, 3, 4, 5. Change it to 5.
2, 2,
Okay.
3.
How many you got? 5. How many? Okay, there should be 5. There should be 5. Everybody got that? All right, so you have N-hexane. Put a little check mark, N-hexane. Then you should have 2-methylpentane, 3-methylpentane. Now we'll get on to butane. Let's take a look at butane. We could put them on 2,2-dimethyl and 2,3-dimethyl. Is that what everybody has? All right, erase this, and let me give you a really big challenge. Erase this. You're gonna need a little more space. We're gonna do all the isomers of heptane. Heptane. All the isomers of heptane. Now you might wanna, you can build them and name them as you go, and if you name as you go, you'll see where there was a repeat or something like that.
That might be a better way. Let me try it. Heptane, and then 6.
You put it there.
It's yeah, the same as theirs.
Okay.
These 2
Okay. Now, are there any more? Are there any more hexanes?
3-methylhexane.
All right. Look at her mind working there. Look at that.
That's the same thing.
Oh.
That's the same thing. as this
Oh,
one.
wait. 1, 2, 3.
Oh,
1, 2,
this
3.
is the same.
Ah,
Yeah.
okay.
Oh, 'cause
What's your, how do you know you're not doing repeating? You guys just, how are you guys doing this as a team?
we're just
You just,
naming them
you
as
just
we
thinking
go.
out together, all 4?
Yes.
Okay.
So if I put it here, it's gonna be 3.
Let me go down there.
I got it. That's my
So
one
if you
job.
write tiny enough, it might work?
Yeah.
Okay.
That would be 3 diagonal.
Well, that's what they're doing, so there are 9 of them.